Okay, thank you and sorry for the delay. In theory, my student David should be here, but at the end it wasn't possible, so I'm going to do the talk about this work. I'm really from the computer vision community, not from the machine learning, and we just take your results from the machine learning community and use them. So I'm not going to show theory or whatever, just an application, okay? This is the outline of the presentation. First, I will introduce the application. After, I will introduce what we call target domain, also the source domain, and what we have done for doing what we understood as domain adaptation. And finally, the conclusions. Okay, our application is in the field of human detection. This is useful for many applications like pedestrian detection, applications in multimedia, surveillance. In fact, we are here in the field of driver assistance. So, in our initial work was to detect pedestrian from a moving car. Well, if you look to the literature on pedestrian detection, the state of the art relies on discriminative learning. This means that you need to provide samples, positive and negative samples, to build up a classifier. So you have these samples, and then they are you extract your features. There is many people doing defining new features, defining new learning machines, and at the end you end up with a classifier, which means that if you have an image and you take a small window of the image, the classifier is able to say if inside this window there is a pedestrian or not. Okay, this is it. And then with this, what you do is, given an image, you travel along the image with certain windows at different scales. You get even multiple detections from the same pedestrian, and then you summarize them in a single detection. This is more or less what pedestrian detection is about. Of course, there are more things like tracking and other things, but for the talk of today, this is it. Okay, let's go to the target domain in this case. Okay. For us, the target domain are images like this one, that were taken from a car. And for doing our experiments, we started with, or we used a database which is publicly available from Daimler, the automotive company. Okay, and these are examples from this data set. You have a training set and a testing set. Okay. The problem is that to get these examples, to make the training, you have to do manual annotation. Manual annotation at least means to put a bounding box for the pedestrians. Okay, I have done this myself. It's quite time-consuming, subjective, and quite boring thing. Okay, so. Well, the current solutions for that, in fact, is to use web-based annotation tools, which means that, well, you have many annotation from many people because you can pay very small prices, but still you have to deal with annotation errors because someone misunderstood the task, there are malicious workers, there's some activity, whatever. Also, you have to devise reward strategies, annotation guidelines, and so on. So this is one way, but we don't want to follow it this way. So we wanted to explore a very different thing. And this brings us to the source domain. Our idea here was the following. Okay, in fact this is an idea that was around for 10 years in our head, but yeah, we couldn't implement it before. The idea is the following. We know that computer animation is providing more and more realistic world, virtual worlds. For instance, if you look at the last video games, many of them are quite realistic. Okay, so our idea was, okay, can we close now the circle in the sense that computer animation was based in reality to build these generative models, realistic generative models. Can we now learn in this virtual world and apply our classifiers in real world so that we close the circle? And this is what we did in a previous work on CVPR 2010. We built a virtual city. We traveled through this city with the vehicle, a virtual vehicle, of course. Then we took pictures of the view from the vehicle. We have automatically ground truth, pixel-wise ground truth, which is very hard to obtain by hand. And then we build a classifier based on this virtual information. This is the classifier, and then we plug it in the classifier in a standard pedestrian detection pipeline. Okay, and then we put here the real world images, and we get our results. Okay, this is an example of this virtual city. Okay, so it's kind of realistic. It's not the most realistic possibility, but it's quite okay. And here is how we get the data. Well, actually, this is from
much less boring.
What?
It's much less boring than.
Yes, yeah, but actually, this can be done by the video game itself. It's not necessarily the But what happens here?
That's a funny.
Yeah. What happens here is that this actually comes from a video game that was for shuttering, and we couldn't go inside the code of this video game, so we just changed the gun by the wheel. Sometimes it's the same for some people, you know, and we did like this. Okay, and from that we get these results, this data set. So, okay, and then I know that, you know, Big Bang was okay for the universe, but we like to start always from the basics. And then we said, okay, let's go to use one baseline, which is not the state of the art in pedestrian detection, which consists on using the histogram of oriented gradients by Dalal in CVPR 2005 as features. These features, for those that are not familiar with the computer vision community, are trying to codify a kind of global shape of the person. So it's not texture, but mainly shape. Okay, and then using also a linear SVM for doing the classification in this feature space. Nowadays there are better feature spaces, and maybe here other kernels, but this is a quite Rose baseline in the sense that new stuff many times is just to add new things to this. So this is there, the still is there. And not only for pedestrian detection, but for object detection in general. Okay, then we did our experiments, which this is a typical evaluation procedure for us. Here we have the false positive per image, which means if I look to an image, how many windows says our method that are pedestrian but are not. And this is the miss rate in percentage, which means how many pedestrians I miss. Okay. Usually we use this range of the curve because it's the most interesting one for our type of applications. And here what we have, this versus means train it with Daimler data, test it with Daimler data. And this means train it with the virtual examples and test it in the Daimler data. And this here, and this here is the area under these curves. Okay, so basically what this number says is that, well, this first idea works. Okay, because we have basically the same performance without doing any annotation. okay, since this was good, we said, okay, let's go to another type of application, which means let's use a different data set. For instance, this in real data set, which is different from the previous one, in the sense that these are pictures from the holidays, and the previous one were images from a car. Okay, and in this case, what happens is that, well, we did exactly the same experiment, but yeah, we have a gap of 7% on the performance. These cubes. So in this case, exactly the same didn't work, or didn't work too well, because after all, this is not that bad result. This is very far from random. Okay. Okay. Then we were thinking, what can be the problem? Maybe the problem is that we are using virtual data. And then what we did after is to use Daimler data to test, to train a classifier and test in the real data set. And then we saw that, in fact, for the Daimler data that is coming from real world, it happens the same than for our virtual data. So it was something like, okay, this is not due to the virtual data, it's just because the data is different. It doesn't matter if it comes from the virtual world or from the real world. Okay? Okay. And then we started what we call the Google descent. That means that we have this problem and then start to look in Google for this kind of literature. Let's see what is doing other people with similar problems. And we got a paper from this paper of frustratingly easy domain adaptation, and then we read it and we said, okay, this is in fact our problem. We didn't know, but we have a problem of domain adaptation. Okay, and well, this led us to this work on domain adaptation. What happens here? If I look to the 3 data sets we have been working with, it turns out that the virtual and the Daimler come from a series. This means that the typical pose of the people and the typical background and so on is more similar between these two than with this third one. Why? Because here you have, for instance, pictures from the beach, pictures from indoors, pictures from the snow, and the backgrounds are different. The pose of the people is different because you don't stay like this in the street when you are walking. And here they were posing for the photograph and so on. So you have difference here in the humans. You have difference in the backgrounds, and also you can think that this is a different sensor, this is a different sensor, and this is a different sensor. The camera, I mean. And this issue of the camera is quite important because, yeah, we started to work 10 years ago with this kind of cameras, then we moved to another, we moved to another, we moved to another, and we are constantly changing the camera because a different person a different company wants a different camera. And this happens with robotics in general. You start as you can and you go in progress, but you are changing and changing the camera. And yes, by that time we also were looking for information on computer vision and domain adaptation. We found some papers here, but not too many, and now there are more. I have seen all this in the walls, and probably more and more will come. But by the time we started with this, there were not too much information. Okay, and then what we proposed was a very pragmatic framework. I mean, we don't have bounds on the error, on things like that. We just tried something from your literature and see what happens. In fact, we call our framework VELA, which means Virtual World Annotation, Yet Learning Adaptively. And we use this name because, you know, it's the main character of the saga of, I don't know if you know the Earl of Children. You know this saga? And Ayla is the main character. Is a Cro-Magnon woman that grows with the other Cro-Magnon, and the Neanderthals, and then have to go again with the Cro-Magnon. So this is not not the end of the story, but the message is she has to adapt to a very different way of living and a very different language. So it's why we use this. Okay, and in which what is going on here? Well, first, again, to make things simple, we started by supervised domain adaptation. So we will assume some labels. To do that, we know that there is correlation between the targeting and the testing domain, because even the gap was big. 35% of miss rate means that there are correlations there. Okay, then our system has two major stages. In the first stage is just what I have explained before. Train with virtual data, test on real one. But now, what we do is, in this domain adaptation stage, for us has two things. One thing is to collect samples from the target domain, and another thing is how to mix the virtual and the real samples in what we call the cool world, because this movie that have both things. Okay, in this case, what we did was to follow an active learning procedure. What means that the results of this detection are presented to a human oracle, and then the human oracle labels the missing humans. Okay? Also, we got some background examples from the target domain. Okay? This is basically the idea. So in this work, we focused more on how to collect the real data. Basically, we follow a batch mode active learning. That means that we process the whole sequence, not one image and retrain, one image and retrain. Here, well, the oracle, what it has to do is given an image, just to say if there is there are pedestrians or not, and if there are pedestrians and someone is missing, then you have to annotate them. Okay. Okay. For the experimental settings, what we did is the following. First, I must say that the active samples will come from the INRIA training data, not from the testing. So we are really using the same data for training. Okay. In order to be able to do as many experiments as we can, of course, we cannot have a person annotating there for each experiment. Then what we did is a simulation of the oracle, because we have all the training data of INRIA annotated. We can sample this data, simulating the active behavior or the random behavior. Okay? And finally, we restricted ourselves to label as maximum the 25% of the real world examples of the training of INRIA. Okay? Because if this is the 100%, then nothing has sense, because then we are annotating, which is what we want to avoid. Okay, and here come some results. First, we did some tests on how to decide what is a detection. In other words, the threshold for the output of the SVM. Okay, and we found that putting here the threshold in the -1, just in the border, in the limit of the uncertainty region of the SVM, then the oracle annotates the positive examples that are here. Okay, and usually when people use active learning in this context, where there are no target and source domain. Is training and testing is from the same domain. What they do is to annotate examples here inside the ambiguity region, but we didn't do that. Just example here. Okay, and then by doing that, we got this result here, which is already pretty similar, or well, in this case even better than by training with in real data. Okay, so we captured the same cube. Okay, and this is, by the way, this is the number of annotated pedestrians. In this case, even with 27 examples, which is the 2% of the data set, we already improved from 36 to 33. With the 8%, which are only 97 pedestrians, we go to the 30 and so on. So, annotating just these few pedestrians, we were already able to reproduce the same results. We did more experiments. For instance, what happens if we only add positive examples from the real world? And then in this case, we got worse results. Okay. What happens if we only add negative examples from the real world? This would be very nice to do only that, because this would be not annotation at all. But in this case, also it goes worse. And finally, what we did was how compares this by with the random annotation. And still, the active way is better than the random, but even if it is the same, we prefer the active, because when the oracle see the result, is able to do similar things. You are like training the oracle also how to annotate the missing things, because you are showing him or her the annotations of your algorithm. Another thing is that probably the INRIA training data is not as random as it could be, because it was annotated, I think, by a person that was working in the algorithm for detecting the pedestrian. So it was an expert on vision. So it's why I think that it's not that random, the annotation. Okay. And finally, we started to throw active examples. What happens if I annotate less? And then, well, this is the result of the 100% that we have seen up to now. And well, it seems that even throwing away the 25% of the whole possibility, we still do good. But beyond that, yeah, we start to go worse and worse. Okay, so this is all experiments. This is the final thing on the experiments, is that we compare. We did an experiment that in fact has no sense for us, because it consists on training using our virtual data and the in-real data, but has no sense for us because this means actually to label the data, so it has no sense. But it's just to see what happens. And if we just mix together the whole data, we didn't get very good results with respect to just using the annotated examples using the active learning procedure. Okay, so it's kind of just blindly mixing everything, doesn't work that good. Then we look at what type of just two more. What type of examples were annotated? And we can see that from the available indoor persons, the 52% were annotated. From the beach, the 28, from the snow, the 35, which means that actually these scenarios were not in our virtual data. So it's kind that we are really providing new things by the active learning. Okay, I will skip this then. Just in conclusion, Well, we think that learning from virtual world is a promising paradigm for building even appearance models, like the pedestrian or other objects. Also, that virtual world can suffer data set shift as any other data set. And then that domain adaptation techniques, even this simple thing that they have used, allow to adapt this real and virtual and real world. And just to finish, just saying that we are from another community, we came here just to learn about. We are open to collaborations and give thanks to the organizers, because I'm also organizer of workshop, and I know that it's quite difficult. So thank you for your attention.